We'll start first section on probability and decision making. Decision making is an area where probability in Bayesian learning is heavily used and applied. And we will go through some motivating examples, which I think also very interesting, where we show how Bayesian learning can be used to make decisions under uncertainty. And we'll start, of course, by talking about the basic notion of probability. And we will cover the axioms. Axioms is set of basic rules, and principle of coherence states that a decision maker has to make decision while following those basic set of rules, so axioms. And Kolmogorov was the first person who put this set of axioms together. He applied approach that was used in algebra and geometry many years ago, where a set of axioms would be developed, and most of the facts about probability can be derived from those basic set of axioms. And so this was done in 1930s. So again, it was in algebra and geometry, it was done way earlier. And putting axioms together was a way to make probability to be a field of mathematics, or have a rigorous mathematical study of probability. So let's talk about those set of axioms. They are relatively simple. Event A, if event A is certain to occur, if we are sure about it, then we say it will happen with probability 1. Event A is either to occur or not to occur, and so the probabilities of those two have to sum up to 1. And the third rule says if two events are mutually exclusive, both cannot occur simultaneously, then probability of A or B happening is just the sum of individual probabilities. So you should remember that OR is equivalent to plus. So whenever we have OR statements, we sum up probabilities. And the fourth rule about joint probability says when events are independent, and we'll talk about this notion of independence a little bit later, meaning probability of A and B is to be calculated, then on the independence assumption, this is just a product of the probabilities, probability A and probability B. So when you see AND, this is equivalent to multiplying individual probabilities. And of course, we are talking about events here. And in the first lecture, we'll be talking a little bit more about events. But through the rest of the course, we'll be talking about random variables mostly rather than events. And let's talk about what random variable is. So random variable. Let's talk about random variable. For short, RV. It's basically a tuple or a duo. So random variable is defined by domain. So it's a set of numbers for which this random variable exists. So it's a subset of Rn, and a function which we call density function. Or let's say probability function, probability density function, probability. Or PDF for short. In PDF is just a map. It's just, so PDF, we're gonna call it function f. Okay, so that's our PDF. And PDF maps domain to a number between 0 and 1. Okay. So that's it. So for each value from the domain, for each possible value of a random variable, we have a probability density function that just tells what's the density associated with this specific value, and it's always number between 0 and 1. And another rule that this PDF function has to satisfy. So, and let's call this random variable, we're going to call it x. So if you integrate this function f with respect to this variable x, then it basically has to be equal to 1. Um, And so it's either f will be used to denote density function, or more often it's going to be letter p. So p of x, so p will be the density function of a random variable x. And another agreement I want to make going forward in this class, you often will see textbooks distinguishing random variable and having it as capital letter x, to be a random variable, and small x to be a sample value of this random variable. And also you will see small p to be the density function, and bp to be the probability function. So in this course, I will not make this distinction. And usually from the context, it's relatively clear whether we're talking about random variable or a sample from this random variable, and whether we're talking about the density function or the probability function. So we're always going to be using small p, and we're always going to be small x. For example, you're going to see notation something like this: x follows p of x. So this notation means that random variable x follows distribution specified by the probability density function small p. Okay, so this is kind of meaningless notation, but it's convenient. So we'll use those type of notations. But I'll remind you, once we start heavily using this type of notations, I'll remind you about this agreement. All right. So let's talk about conditional join and marginal distributions. Um, so we always whenever we try to use probability to describe outcome of more than one event or more than one variable, we need to be able to measure what we think will happen with one variable relative to another variable, and we're going to be using two ways to do that. One way is through joint probability. So joint probability is the probability that random variable x takes a value small x, and random variable y takes small y. And this is called joint probability. And I just mentioned the notation shortcut that we're going to avoid capital and small. So using our shortcut here, shortcut notation, we're just going to be writing small p of x and y. So this is stands for, so this equivalent p, capital P, x equal x, and y equal y. So it's the same thing, okay? All right, so that's the joint. And the conditional probability is probability that random variable x takes value x, given that we know that y takes value y. And hopefully by now, since this is a PhD course, you should be somewhat aware of those notions. But again, we'll talk about joints a lot and conditionals a lot. So even if you are rusty on those things, that hopefully it will become natural for you by the end of this course. And marginal probability is the probability of a single variable calculated from the joint. And we'll talk about how to calculate marginal probabilities later. All right, so the relationship between joint and conditional, probability of x and y, is the probability of y given x times probability of x. And since the joint is symmetric, this one is equal to p of y x. So it's also equal to the probability of y times the conditional of probability x given y. All right. And the way to calculate the marginal from joint is you simply sum up all the joints with respect to the variable you try to integrate out. So the joint with respect to x, you have to sum out y. And if you want to calculate the joint with respect to y, you just have sum out x. And of course, so this applies to discrete probabilities when x and y takes countable number of possible values. So this applies to discrete. And when you want to calculate marginal for a continuous variable, you just replace summation sign with integration sign. So for continuous variable, so continuous random variable, if you want to calculate, so given, if you're given joint density over two variables p of x and y, and you want to calculate marginal over x, you just take this joint over x and y and you integrate y out from it. Okay, so again, you just replace summation with integration. That's all it is. And now let's talk about the Bayes rule. The Bayes rule follows from the relationship between conditional and marginal. You remember that the p of y x equals to p of x given y times the probability of y. Now, if you divide both sides by p of y, you're gonna get x conditional on y is just joint of y and x divided by the marginal of p of y. And of course, p of yx can be written down as p of y given x, probability of x divided by the probability of y. So what happens here? On the left-hand side, we have a conditional probability over x given y, and we calculated it from three different quantities. So the first quantity is this one, probability of y given x, and this is called likelihood. And if it's not clear why, it's going to become clear why it's called this way. Likelihood. The second value is p of x. So that's the marginal over x. And this one is called prior. And the bottom one, marginal over y, is called marginal. And why those names are used, and we're going to jump a little bit ahead here. Usually in Bayesian learning, we apply this rule in the following settings. We have some parameter to estimate, some parameter of a statistical model. That we want to estimate. And we're going to call this parameter theta. So if you're talking about a linear regression model, then theta is just going to be a set of the beta coefficients. If you're talking about estimating parameter of the normal model, then it's going to be mean and covariance matrix of the normal distribution. So depending on your statistical model, you're going to have a set of parameters theta to estimate. And you also have data. So you have some observations. And you have what is called likelihood function. And the likelihood is probability of observing this data set D given the parameter theta of the statistical model. Okay. But likelihood is not what we're interested. What we're really interested is the distribution over parameter theta given the observed data set. And we can calculate this using the Bayes rule. So it's just the probability over data given data. That's the likelihood. Probability of observing data given the parameter of the model times p of theta. And p of theta is our prior assumption about what value of theta we need to have and divided by the marginal probability over the data set. Okay, so that's why those names are used in the Bayes rule. All right, and now when we want to calculate, now we just go back to the formula. So we have probability of x given y. This is general formula, and this is just probability of y given x times p of x divided by the marginal. Again, if we want to get the marginal, we just have to sum out one of the variables. That's what we do here. And again, if you want to do it for continuous variables, it's going to look exactly the same. P of y given x, p of x. But instead of the sum here, you're going to have an integral here, p of y given x times p of x, and you integrate with respect to x. Okay, so this is the case of the continuous variable. I'm going to isolate it in a frame so you don't get confused with a discrete variable. So Bayes rule allows us to calculate conditional distribution from joint and marginal. And usually you will be given the quantities on the right-hand side, and you need to calculate the posterior distribution over x, which is on the left-hand side. And sometimes you don't really have those quantities. Sometimes you have to calculate those. So for example, this one you usually will have to calculate the marginal. And again, jumping a little bit ahead, when you have a countable number of small number of possible values of y and x, calculating marginal is easy. However, when you have them the number of possible values of y and x to when they're continuous, this integral is not necessarily an easy integral to calculate, and then you might have to do some numerical approximations to this integral, and that's what this Markov chain Monte Carlo techniques gonna do for us. All right, so but let's look at the demonstration of the Bayes rule. And one of the fallacies is to confuse p of x given y and p of y given x. They're generally different things. Here's an example which I hope you will remember. Probability of given that I play an NBA, given that I'm an NBA player, probability that I practice hard equals roughly close to 1. So it's you can hardly imagine an NBA player that is a slacker, who is a slacker and doesn't practice hard. However, the opposite is not true. I can practice as hard as I want, or I can, but the likelihood that I get into ABA is close to zero. I just simply don't have the right physique. I don't have the stamina, and I don't have the height. So chances of me getting and relatively old for an NBA player as well. So chances of me getting into NBA is close to zero. So one probability of x given y is not equal to probability of y given x, and why is that? Why this value is close to zero? Well, the main reason is that the prior probability of playing an NBA close to zero. Remember that the probability that I can play an NBA, given that I practice hard, is the probability of practicing hard, given that one is an NBA player, times the prior probability of playing an NBA divided by the total probability of practicing hard. So what it means here, what is this probability of playing an NBA? What is prior? It basically means that if you randomly pick people on the street and you ask this person, are you playing in NBA? Then most of the times you'll hear no. So I probably can make a guess. You can go to you can go to Chicago or a DC center, and you can spend 3 4 days stopping people on the street and asking if they play in NBA, and most likely you won't hear a single yes. So to begin with, there is a very low fraction of people that play in NBA. So the prior chances that someone can play in NBA is low, and so this number is very close to zero. And of course, we talked about this number probability of practicing hard, given that you play in NBA. This number is relatively close to one, and then probability of practicing hard, I don't know, so they may be whatever. So that's just a proportion of people that can practice hard or do practice hard already in the population, and probably there is, I don't know, still relatively small number of people who practice hard basketball. So maybe 1% of the people, at least in the United States, they practice hard. Either basketball or, let's say, some other sport. So let's say if you can practice hard uh, hockey, you also can practice hard basketball. So let's say 1 out of 100 people do practice hard one of the sports. Um, all right. So hopefully that shows you the power of the base rule. Now let's talk about the notion of independence. We say that two random variables x and y are independent if knowing anything about x doesn't tell us anything about y. In other words, probability of y given x is just the probability of y. So this conditional here doesn't say anything about y. So example, tossing coin twice. If you get ahead on the second toss, then it doesn't tell you anything about the probability of observing tails on the first toss. Those two independent events. And another way to write independence, you remember in the uh, equation that relates the joint and the conditional. Since probability of y given x is just x, probability of y under the independence rule, so it just becomes probability of y times the probability of x. So, and again, that's one of the axioms that we talked about. If you have two random variables that are independent, then the joint probability is just the product of individual probabilities. Okay, here's a simple example that demonstrates how simple rules of the probability can be used to design a winning betting strategy. So now we're going to the field of decision making and using probabilities to make decisions. There's nothing Bayesian about this rule. It's actually very simple, the way it works. So and you can click uh, on the link, and you can read the MIT Tech Review article about this group of people. They were using this bias in the way that bookies set up the odds, and the bias sometimes exists when you have an underdog that is heavily loved by the fans. So if you follow baseball, for example, you know that in Chicago there are two baseball teams, White Sox and Cubs, and Cubs has been an underdog for many years, and White Sox was relatively strong baseball team. However, Cubs fan base is much stronger, so somehow more people follow Cubs, and when they place bets, for example, when White Sox would play against Cubs, a lot of the people will place a bet that Cubs will win. And so if Cubs indeed win, if it actually happens, then bookies will actually lose a lot of money because there were a lot of bettors that put a bet on the Cubs, and the odds are in favor of White Sox, so the payouts will be relatively sizable. And bookies try to hedge themselves against this big loss, and they take the objective odds and they bias it a little bit towards the underdog that has a lot of fans. So in this case, let's say, we have odds 4-1, meaning that if five baseball matches to be played, then Cubs are expected to win one and Sox are expected to win four. So what they will do, they say, okay, maybe instead of 4-1, so this, let's say that's an objective odds calculated by bookies. That's what they think is the best possible guess about the outcome of this game. Then what they will do, they will go and actually put a slight modification, slight adjustment to this. So instead of 4-1, let's say they say 7-2. So they put a little bit more weight on the Cubs, and that's basically a hedging strategy, again, to prevent a big loss. And what this group of guys did, they would look for those situations when the hedging strategy was applied to the betting odds. And the way they identify a bookie that applied this hedging adjustment is they look at all the betting odds and then they take an average. So they calculate, they take betting odds from all the bookies companies they can get it from and different bookies. So let's call it an XI. So that's the betting odd from bookie I. And then they just calculate average. So they sum up all those betting odds from all the bookies. And then they calculate then they solve the simple problem. So they find index J. They basically find a bookie that deviates the furthest from the average. And then they assume that this bookie J is hedging. Meaning that the odds that this book is using is not objective. And if you bet against those odds, that you actually in favor. And that's all they did. So they just calculate the average, calculate the distance from the average to all the odds from other bookies, and they pick the one that deviates the most and bet with that bookie. And the authors of this article from MIT Tech Review actually did a computer simulation of this strategy. And what you see, this blue line here, is the computer simulation, a result of this computer simulation. They took historical data and they applied this betting strategy to the historical data. And what you see is the growth of the wealth of $1. So you start with $1. And after placing 7,000 bets, your $1 becomes $30,000. So you multiplied your wealth by 30,000 after placing 7,000 bets using this simple strategy. And the red lines that you see is just random betting, meaning that you just flip a coin and you decide for which team to bet. And of course, in this case, you're going to be losing half of the times and you're going to be winning half of the times. So this strategy is pretty clear and obvious, the result of this strategy. And it's also quite clear that this simple strategy that looks for hedging against the bookies is dominating. Okay. So let's talk about odds since we started talking about betting. We can express probability in terms of odds, and odd is just 1 minus probability of A divided by the probability of A. And you can reverse this formula and you calculate probability from the odds. Probability of A is just 1 divided by plus 1 divided by 1 plus the odds. And let's look at an example. For example, if odds is 1, then for every dollar you bet, you'll get a payout of 1. And in other words, it's an event with probability 1/2. And you have odds equals to 2 or 2 to 1, then for every dollar you bet, you'll get back dollar that you betted plus $2 on top of it. So you get $3 back. And then the probability of winning is 1/3. So the way you can interpret odds, so example, you have odds 2 to 1. It means that if game is to be played 3 times, then you expect to win 1 time and lose 2 of the times. Okay. Why do we use odds? Sometimes it's more convenient for mathematical reasons, and sometimes it's more convenient for the reasons of presenting information, especially when we talk about low probabilities, low probability events. So when you tell somebody that probability is 10 to the negative 6, this is a very hard number to assess, right? On the other hand, so the odds of this will be, so it's basically 1 divided by 10 to the negative 6. So it's 10 to the power 6, essentially 1 in a million. When you say probability 10 to the negative 6 versus odds is 1 in a million, for some people it's more intuitive and clear when you say this information in terms of odds rather than probabilities. And I think odds are quite convenient to use when you talk about those low probability events.